Bismillah. Bismillahirrahmanirrahim. In today's lecture, which is a series of lecture of IC engine, we will be talking about chapter 5, air and fuel induction. It is in three parts. So in last chapter, we have studied regarding the fuel in detail. Now see how the air and fuel is coming inside the combustion chamber. Now, the object of the intake system is to deliver the proper amount of air fuel. The object of the intake system is to deliver the proper amount of air and fuel accurately and equally to all cylinder. If you have a multi-cylinder engine and you have to induce the air fuel system into it, should have an intake air system or intake manifold that should deliver proper amount of air fuel accurately and equal to all cylinder at the proper time in the engine cycle. So it is very, very important that you should have a proper amount of air fuel mixture. The stoichiometric ratio should be ideal. Okay. And it should accurate and equally to all cylinders, means which is nearer, they should not get the more, and the furthest far away should not get the less or least one. And at the proper time in the engine cycle, at what time they should be injected inside the cylinder. Okay, so this is very important. Once again, I read this. The object of the intake system is to deliver the proper amount of air fuel accurately and equally to all cylinders at the proper time in the engine cycle. Now, air and fuel induction, main parts of the intake system. We have a intake manifold, we have throttle, we have intake valves, we either have fuel injectors or a carburetor. In modern vehicles, we have fuel injectors. In old conventional vehicle, we were having carburetors. So now injector arrangement, there are three types of injector arrangement. One is close to the intake valves, multi-port fuel injection. At the inlet manifold, throttle body injection, and direct injection in the cylinder means direct injection. So we will study in detail. Now, intake manifold is a system designed to deliver air to the engine through pipes to each cylinder called runner. But sometimes the intake manifold also get the air fuel mixture. Sometimes it is only the air, it depends upon your design, and sometimes it is air fuel mixture. So the intake manifold is a system designed to deliver air to the engine through pipes to each cylinder called runners. How it look like? So this is like this. This is your air intake manifold. This portion is connected to your engine as there are four openings. So it means the engine has four cylinders. So for piping arrangement, these four piping arrangement is called runner, and here is the plenum. The air fuel mixture is coming to this portion and divided into equally and accurately in all the four pipes, the runners. So the intake manifold is a system designed to deliver air to the engine through pipes to each cylinder called runners. Now, the diameter should be large enough to offer low flow resistance. The diameter of this runner or this pipe should be large enough so that there should be low flow resistance, which reduces volumetric efficiency, and should be small enough to produce high velocity and turbulence to improve fuel carrying capacity and increase evaporation and air mixing. So we have to have some compromise situation here, that either it should be large enough to have low flow resistance, but it will reduce the volumetric efficiency, and it should be small enough to produce high velocity and turbulence for better mixing of the fuel with the air to increase the carrying capacity and increase the evaporation and air fuel mixing. So diameter is of that much of critical value. Now, even distribution. The length of the runner and its diameter should be sized together to equalize as much as possible the amount of air fuel that is delivered to each separate cylinder. Now, this length from the palm to this opening of the cylinder, where the opening to the cylinder is, this length is also an important. Dia is also important, and this length is also important. So, for the even distribution of the air fuel mixture into the cylinders, the length of the runner and its diameter should be sized together to equalize as much as possible the amount of air and fuel that is delivered to each separate cylinder. So we have to take in account the dia of the runner and the length of the length of the runner, so that they should be evenly distributing in each cylinder, and they should having a high velocity and turbulence and low flow resistance. On SA engines, airflow rate through the intake manifold is controlled by throttle plates, butterfly valve usually located at the upstream. So in an SI engine, the airflow rate through the intake manifold is controlled by a throttle plate, that is butterfly valve, usually located at the upstream end. So a fuel addition. Fuel is added to the inlet air somewhere in the intake system before the manifold, in the manifold, or directly into the each cylinder. So there are three options available for us regarding the fuel. We can either inject it somewhere in the intake system before the manifold, or in the manifold, or directly into the cylinders. Additional further upstream or early addition. If we do upstream or early addition, with more time to evaporate and give proper air fuel mixing, we achieve this advantage, but reduce the volumetric efficiency. Problem to get air fuel consistency. So we will get these problems. Asymmetric of manifold and runner length variation. So there are three options available for us for adding the fuel in the air intake. So somewhere it is before the manifold, in the manifold, or directly into the cylinder. And if we add the fuel in upstream or early addition, then we have this advantage and this few disadvantages. Now, different manners of fuel flow for early additions. Very small size fuel droplet mixes with air and flows with it following the streamlines better than large droplets. Large size liquid droplets flows with different velocities from the smaller droplets due to a higher mass inertia deviating from air velocity and more than smaller one. So the fuel having a mixture of molecular size, the smaller size and the larger size. The smaller size will flow more rapidly and the larger size will having a less velocities. So liquid flow in a thin liquid film along the wall. As it's a liquid, they will be creating a thin liquid wall, thin liquid film along the wall. So gravity separates some droplets. Other droplet strikes the wall where the runner executes. Above mentioned point 2 and 3 creates problem for same air fuel to all the cylinders, whereas 3 also creates problem for precise throttle. So the length of the runner and bend will influence the amount of fuel gets carried away by the airflow. Now, knock problem. Gasoline components have different evaporation temperature, as we have seen in chapter 4. There should be three temperature mentioned on your fuel barrel. First one is 57 degrees Celsius, on which your 10% of the fuel should evaporate. Then we have 81 degrees Celsius, on which your 50% of the fuel should evaporate. Then we have 103 temperature value, on which your 90% of the fuel should evaporate. So gasoline components have different evaporation temperature. The air fuel delivered to each cylinder will have different composition. So basing on the molecular size and the evaporation temperature, The air fuel delivered to each cylinder will have different component composition. Different throttle position will give different pressure and changes the evaporation rate of the various fuel component. Now, if you have a throttle, you can have a throttle position that is varying in a second and in a time frame that will also change the pressure differential in the intake manifold. So the pressure differential is changed, so the evaporation rate is changed and of the various fuel components. So due to above all these factors, different evaporation temperature, different composition, and different throttle position. So the knock problem will be different in each cylinder. It is not uniform. Remember, in first cylinder, the noise will be different. In second cylinder, the knock problem will be different. In the third or fourth cylinder, it will subsequently be different. Now, will not be uniform. Now, the volumetric efficiency of an SI engine. It is desirable to have maximum volumetric efficiency in intake of an engine. So the more the volumetric efficiency of an engine, more the power. This will vary with engine speed. One factor which affecting the volumetric efficiency is the engine speed. There will be certain engine speed at which the volumetric efficiency is maximum, decreasing at both higher and lower speeds. So it is not that we are increasing the accelerator or the engine speed and we are getting the volumetric increase in volumetric efficiency. At some point, it will be maximum, then it will be dropping again, as we have seen in the graphs in the previous chapters. The type of the fuel and how and when it is added will determine how much the volumetric efficiency is affected. Very important. The type of the fuel and how and when it is added will determine how much the volumetric efficiency is affected. So this is very important for your having the volumetric efficiency. Now let's see volumetric efficiency as a function of engine speed for typical SI engine. On our x-axis, we have engine speed. On our y-axis, we have volumetric efficiency in percentage. As the speed increases, the volumetric efficiency increases. At certain point, it is maximum. But the speed is increasing. Now the volumetric efficiency is decreasing because of certain other losses. So we get the peak value. Before peak value, we have lower value. And after the peak value, we also get some lower value. So it is not that you are increasing the speed and the volumetric efficiency is increasing. It's a specific speed on which you get the maximum volumetric efficiency. Now, the volumetric efficiency depends on following factors. Those are fuel, heat transfer, valve overlap, fluid friction losses, choked flow, closing intake valve after VDC, intake tuning, exhaust residual, and EGR, the exhaust gas recycle. We will study all these factors in detail. First, the fuel. It affects the volumetric efficiency. Volumetric efficiency is always less than 100% due to fuel addition, which will displace some incoming air. So the volumetric efficiency is always less than 100% because it will displace some of the air which is coming inside the intake manifold and then going to the cylinders. System with carburetors or throttle body injection add fuel early in the intake flow and generally have lower overall volumetric efficiency. So if we are injecting or mixing the fuel with the air early in the upstream, then we have a lower overall volumetric efficiency. Now, if we have a multi-point injector, have better volumetric efficiency, no air displaced until after the intake manifold. Fuel evaporation does not occur until the flow is entering the cylinder at the intake valve. Direct injection system has best volumetric efficiency. First, I will explain this. If we have this run arrangement and we have multiple point port injection, some here, 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 here. So we have multiple point injectors which will have a better volumetric efficiency because the air is coming into the intake manifold. So no air will be displaced until after the intake manifold. Fuel evaporation does not occur until the flow is entering in the cylinder at the intake valve. But if we have a direct injection system, direct injection system is that which we are directly injecting the fuel in the cylinder in the combustion chamber. So all the air is coming inside the intake manifold and then going to the cylinder, and then we are injecting the fuel. And that direct injection system has the best volumetric efficiency. If we are using carburetor or upstream throttle body mechanism or multi-point injector, then we have a direct injection system is having a best volumetric efficiency. Now, late fuel injection manifolds can be designed with large diameter because high velocity and turbulence is not needed and can be operated cooler to give dense air. So one way is this, we have a late fuel injection manifolds that can be designed with large diameter. So diameter is a critical value, but here we are designing with large diameter because high velocity and turbulence is not needed and can be operated cooler to give dense air. Fuel having less air fuel alcohol will have experienced greater losses in the volumetric efficiency. This problem can be resolved by using high heat of vaporization will regain some of its lost efficiency due to the greater evaporation cooling. So this is regarding the alternate fuel, the alcohol, how you can increase the evaporation cooling. Crankcase dilution, which is happening in the two-stroke engines. If the fuel is evaporated too late in the cycle, the small percent of the high molecular weight components may not vaporize. So where they will go? Some of this vaporized fuel ends up on the wall of the cylinders, where it's get past the piston ring and dilutes the lubricating oil in the crankcase. So there will be crankcase dilution. And because of this heavier part molecular weight molecules. Now, heat transfer. All intake systems are hotter than the surrounding air temperature and will consequently heat the incoming air. If the atmospheric temperature is 25 degrees C, but the intake manifold, the temperature is to 25 to 35 degrees Celsius. So the all intake systems are hotter than the surrounding air temperature and will consequently heat the incoming air. This lowers the density of the air, which reduces the volumetric efficiency. Intake manifolds for carbureted system or throttle body injection system are sometimes purposely heated to enhance fuel evaporation. So sometimes we have to enhance their temperature so that the fuel should evaporate easily. At the start, when engine speed is low, air will stay in the manifold for longer time, resulting in more heat transfer and ultimately reducing volumetric efficiency. As the engine speed increases, the air will have to stay less in the intake manifold and the volumetric efficiency will increase. Now, valve overlap. Both inlet and exhaust valves are open for a brief moment at the end of the exhaust stroke at TDC. When the exhaust stroke is finishing, the piston is moving from BDC to TDC. Before TDC, your intake valve starts opening. Okay, so fresh air fuel mixture is coming in. Some exhaust gases can get pushed through the open intake valve but back into the system. Now, there is high temperature, high pressure in the cylinder. We have another opening. The intake valve is open. So some of the exhaust gases try to escape from that side. But the exhaust gases get pushed away through the open intake valve back into the system because we are getting fresh air, and fresh air is denser and heavier, and exhaust air is lighter. And so the heavier air will push the exhaust gases back inside the cylinder. This problem is greatest at low engine speed when the real time of valve overlap is greater. If we have a valve overlap timing is more, means more degree they are overlapping. Then at slow speed, this problem is more. But at the high speed, and when we have a less time for overall overlapping, this problem is less. Fluid friction losses, another point in volumetric efficiency of an SI engine. Pressure drop in air, which is moving in restricted flow passage, is observed, which happens at a high speed ends. Now, it is coming at 1 atmospheric pressure. but due to the restriction flow in the intake manifold, the runners, and the cylinders, we have a restricted flow passage. Is the pressure drop is there, which happens at high speed end. The viscous flow friction that affects the air as it passes through the air filter, carburetor, throttle plates, intake manifold, and the intake valve reduces the volumetric efficiency of the engine intake system. So the air has to pass all these devices, these things which are happening inside, in between the atmosphere and these cylinders. So the volumetric efficiency is reduced. This pressure loss due to viscous drag can be reduced by how we can minimize this pressure loss. Smoothen the walls or rough walls. Smoothen the walls that may be of carburetor, that may be of intake manifold, that may be of your air filter. Avoidance of sharp bends, so there should be no sharp bends. There should be smooth bends. Elimination of the carburetor because a lot of friction is there. Introducing a multi-valve engine, so we should have a multi-valve engine. Reduction in the flow restriction, increase in flow area. So flow area is increased and reduction in the flow restriction. So that's how we can increase the volumetric efficiency by reducing the fluid friction losses. Choke flow. The extreme cases of flow restriction is when choke flow occur at some location in the intake system. Airflow is increased to higher velocities. It eventually reaches sonic velocity at some point in the system, usually intake valves and carburetor throat. This choke flow condition is maximum flow rate that can be produced in the intake system regardless of how controlling conditions are. So in choke flow, I'll read again. The extreme cases of flow restriction is when choke flow occurs at some location in the intake system. As airflow is increased to higher velocities, it eventually reaches sonic velocities at some point in the system, usually intake valves and carburetor throat. This choke flow condition is the maximum flow rate that can be produced in the intake system regardless of how controlling conditions are changed. Now, intake tuning. Gas flows in pulsed manner in intake resulting in creation of pressure waves. So the gas flow means the airflow is in pulsed manner in the intake resulting in a creation of pressure waves. The wavelength of the waves depends upon the pulse frequency and the flow rate. So the pressure waves wavelength depends upon the pulse frequency, flow rate, and flow rate. Length of the runner to be adjusted so that the pressure waves are synchronized, resulting in higher pressure entering cylinder. So we have to cater for the length of the runner. It should be adjusted that so that the pressure waves synchronized, resulting in high pressure entering cylinder. Active intake system, another way of increasing the volumetric efficiency. Single path runner controlled by a mechanical system or dual path runner controlled by valves, oblique secondary throttle plates. So that is the intake tuning to increase the volumetric efficiency. Now exhaust residue. During the exhaust stroke, not all of the exhaust gases get pushed out of the cylinder by the piston. Small residue being trapped in the clearance volume and amount of residue depends upon. So in your exhaust stroke, when piston is moving from BDC to TDC and your exhaust valve is open, most of the exhaust gases, exhaust residue will leave. But some of them will be trapped in your clearance volume around the intake valve or around the piston and valve spacing. So during the exhaust stroke, not all of the exhaust gases get pushed out of the cylinder by piston. A small residue being trapped in the clearance volume and amount of residue depends upon compression ratio, location of the valves, valve overlap, interacts with air in two ways, lowering density of the air by heating, lowering volumetric efficiency. So these are the factors which affects your residual amount, compression ratio, location of the valves overlap. Now the exhaust gases or exhaust residue which is present in the clearance volume of your cylinder will interact the air in two ways, which is the air is coming, fresh air is coming from the intake valve. It will lower the density of the air by heating because its temperature is high and the intake temperature, which is of the air coming in, is low. So it will lower the density of the air by heating and lower the volume. And density is reduced, the volumetric efficiency is reduced. Exhaust gas recycle. No, reduce combustion temperature. So reduce and recycling reduces volumetric efficiency. Up to about 20% of the exhaust gases will be diverted back into the intake manifold, depending on how the engine is being operated. So another method to improve the volumetric efficiency, we take the exhaust gases recycle, and all of the exhaust gases are not recycled. Only the 20% of the exhaust gases will be diverted back into the intake manifold, depending on how the engine being operated. With this, we comes to the end of our first